In our discussion for the shell energy balance with our last example looking at free convection. So in this example, let's assume we have a stagnant liquid layer. So maybe we'll color code that to make it easier for you to understand. So let's say we have a liquid layer in between two parallel plates. Okay, so the blue here is our liquid layer, and the two plates are maintained at two temperatures, T1 and T2. So T1 is the temperature on the right-hand side, which is a cooled plate maintaining at a lower temperature T1. And on the left-hand side, we have a heated plate having a temperature maintained at T2. So you could imagine that in between the two plates, the liquid layer inside would have, if it's not moving at steady state, we will have some linear temperature profile across the plate. So we're going to have temperature as a function of y. So the question is, what happens if, because we know that the density of a fluid is proportional, or is related to the temperature. Typically, at higher temperatures, you have a lower density, and at lower temperatures you have a higher density. So if a fluid is hotter in one place and cooler in the other place, then there is a chance that natural convection might occur. And this is exactly that problem, is that what happens if that difference in buoyancy actually drives a motion of fluid by free convection. Right, so what happens then? That's going to be what we're discussing at the moment, okay? So let's first define some properties of the fluid. So the fluid would have a density rho and a viscosity mu. Okay, and let's say at the heated wall, we have, so let's define this. So this is negative b, and this is b. So at negative b, or y equals negative b, we have T equals to T2, and we have a cooled wall at y equals to b. We have T equals to T1 there. Okay, so we have some assumptions here before we proceed. So first, we would assume T2 minus T1 is small. So basically that means terms containing delta T square can be neglected. Okay. And the second assumption is that the system closed at top and bottom. Okay, so that means if there is going to be free convection, there is going to be continuous circulation. Okay, and third is we are going to neglect end effects. And finally, T is a function of y only. Okay, so in this particular case, we're not analyzing the stability of the system, but we're just going to first, go through that first. We're going to come back to that in other examples, but let's just say that in this particular example, the upper end and lower ends are closed, and we have a temperature gradient here such that, you might have a velocity profile. You're having the hotter fluids moving upwards, and you might have the heavier fluids or the cooler fluids moving downwards. And they are circulating continuously. Okay, so that will give you a steady state. Okay, so if this is our system, how it works, the question would be, how do you analyze the temperature gradient and velocity profile? Okay, so first what we need to do is, again, we start with the shell balance for the energy flux vector. And how would you think the energy is going to flow here? The energy should be flowing in the z direction. Okay, so let's start with that. So first, we have to perform a shell energy balance of the energy flux vector. And so that's happening in the y direction only. So we need to have a slab of delta y thickness. Okay, so what we have is the energy flux vector in the y direction times the cross-sectional area at y minus EYS at y plus delta y equals to 0. So we get the following is dEy dy equals to 0. And again, if we analyze the combined energy flux vector, we have first the convective terms, partial h times Vy plus rho yx times Vx plus rho yy Vy plus rho yz Vz. And also we have the heat conduction in the y direction. Okay, so if we analyze this, again, we don't have Vx. Vx is, well, we might have we don't have Vx. We don't have Vy either. We might have Vz, so we'll keep that. So Vy is 0. So finally, we are left with equal to Q sub y plus tau yz times Vz, and this equals to negative K dt dy minus mu partial Vz partial y Vz. Okay, so we have a thermal conduction term and a viscous heating term, but typically for free convection, this is going to be very small because your velocities are already very small. So for free convection, okay, so we can even just neglect this. Okay, neglect. So basically, your temperature profile can be assumed to be just represented by Q, right? So you have dEy dy equals to dQy dy equals to 0. So you get K dt dy equals to square equals to 0. And then you have a boundary condition of y equals to negative b, t equals to t2, y equals to b, t equals to t1. So finally you get a linear profile actually. So you have t equals to t bar minus 1/2 delta t times y over b. And here the t bar equals to the average of t1 and t2, and delta t equals to t2 minus t1. Okay, so you have your linear temperature profile determined first. by physical reasoning, it should be still a straight line, okay? So using the temperature profile, we are now going to try to figure out the velocity profile. So what we're going to do next is to do the shell momentum balance. The shell momentum balance over slab, or let's just say the shell momentum balance. And the target here is to get the velocity profile. So again, our first question is, how do we define the shell, right? And so let's think about what's going to happen. Is the shell, how is momentum going to be transferred here? Is it transfer in the z direction, in the y direction, or the x direction? Obviously, there shouldn't be any transfer of momentum in the x direction. So let's look at the z direction and y direction only. Okay, so basically, you can expect that there's going to be a velocity gradient in the y direction, okay? Because, you know, you have boundary conditions having, you know, velocity equals to 0 at the boundaries because it's no slip condition. But what happens in the z direction, right? What happens, would you have some momentum transport in the z direction? You are obviously going to have fluid flows in the z direction. So if you're not sure what happens first, maybe we should consider both. And if you want to consider both directions, that means the shell should contain both delta y and delta z. So you might have a shell that looks like this. You have delta y and you have delta z here. Okay, so let's perform our momentum balance. So we have, using the same idea, we will have our combined stress tensor in the y direction times the cross-sectional area at y minus ys at y plus delta y. So this is the y direction. Okay, and this equals to gravity now. So rho gz. Again, we're going to divide all by let's see, L delta y delta z. And we're going to get the following. We're going to get d dy pi y plus d dz pi sub z plus rho gz equals to 0. Okay, and if we analyze the stress tensor, remember, the stress tensor equals to two components. You have the normal stress and the shear stress. So the stress tensor in the y direction having the normal stress component, that's the pressure-driven forces, plus the shear stress, and that equals to what? Equals to the following, which, you know, you can go back to the textbook to see where this comes from. But I'm just going to write it down for you at the moment. So pi negative mu partial Vx partial y plus partial Vy partial x, that's the shear stress term, plus P delta y minus 2 mu normal stress partial Vy partial y minus mu partial Vz partial y plus partial Vy partial z. And if you analyze all these terms, you get that there's no velocity in the x or y direction, so those are disappearing. You only have the z direction left and the pressure term left. So this equals to P delta y minus mu partial Vz partial y. And we're going to do the same analysis for the stress tensor in the z direction. You get P delta z plus rho z equals to P delta z minus partial z partial y. Okay, so finally, what we have is the following. Based on our balanced equation, the differential equation, we have d dy partial y equals to dp dy minus mu d square vz dy square. And we have d dz partial z equals to dp dz minus mu times d dz partial vz partial y. Okay, and you see that again, this is not changing with z, so this term is 0. Okay, and also pressure doesn't change with y. So finally, you have mu d squared vz dy squared equals to dp dz plus rho gz. Okay, and the essence lies in the following: is up to now we're not taking attention to the gravitational term, but that's where actually the buoyant force occurs. That is where free convection happens, right? So important thing here is that rho is a function of temperature. Okay, so when T increases, rho decreases. Okay. Okay, so what we need to do here is rho equals to rho of T, and we will expand rho of T using Taylor series or Taylor series. Okay, so we have about T bar equals to the arithmetic mean of T1 and T2. Okay, so what that means is rho equals to rho at T equals T bar plus d rho dt at T equals T bar times T minus T bar plus etc. And we'll call that equaling to rho bar minus rho times rho bar plus beta minus T bar, etc. And we'll neglect the terms after the second derivative. Here, beta equals to 1 over V times partial V partial T at constant pressure. Okay, so basically rho bar and beta bar are the density and coefficient of volume expansion at T bar. Okay, so we now get the Taylor mode equation of state. which is what? Which is mu d squared vz dy squared equals to the pressure gradient in the z direction plus rho bar g minus rho bar beta bar t minus t bar. Now you see how the temperature profile is going to affect your velocity profile. So you have your viscous force on the left hand side, you have pressure, and you have buoyant force on the right hand side. So buoyant force. Okay, and the next step is we already know the solution for t, right? So t equals t bar minus 1/2 delta t times y over b. So you substitute that back in, you can solve for your velocity profile with the boundary conditions. So boundary conditions are simple. Is that at the no-slip condition, so at y equals negative b, vz equals 0. At y equals to positive b, vz also equals to 0. Okay, so if you solve for that, you finally get the solution. So the solution is actually quite elegant. The solution is your v sub z equals to some combination of constants here, delta t over 12 mu times b squared times y over b cubed minus y over b plus b squared over 2 mu times dp dz plus rho bar g times y over b squared minus 1. Okay, and because the net mass flow is 0 in the z direction, so that means the integration of rho vz dy equals to 0. What that also means is that dp dz should equal to negative rho bar g. Okay, so that means this term is 0. So finally, we have vz equals to rho g beta delta t over 12 mu times b squared times y over b cubed minus y over b. Okay, so that's our final solution. So if we quickly, not going through the details in the math, but just in the spirit of our example here, is that for a free convection problem, typically we can assume that because the flows are typically small, or the velocity is slow or small, so they typically don't affect, let's say if the temperature difference in this example, T1 and T2 are not very different apart, then you can expect that the flow generated will not be causing a huge problem in the energy balance, right? The work associated to shear here is not going to be very significant. Okay, and with that said, then we can kind of assume that the temperature profile is not affected by the velocity profile. Obviously, if you're having a very violent boiling, then you cannot make this simple assumption. But in our present cases, the temperature difference is small enough that you don't have that happening. Okay, so once you have the temperature profile determined, now we can look at the velocity profile by doing a shell momentum balance. And the actual key here is for free convection, you typically want to put your emphasis, you can't neglect or don't neglect the gravitational term here, because the density here is actually a function of temperature. Okay, and that's going to determine your final velocity profile. Okay, so we are going to stop here, and hopefully we'll get into our next chapter, which is shell mass balance, next week.